Hello and welcome to the MAML Manual. I'm Iris.
And I'm Sebastian.
And today we are going to be presenting 9 problems from Meet 3, topic number 2, Exponents and Radicals. Let's jump right into it. Alright, let's get started. So before we jump into some actual problem solving, I'm going to cover a few exponent and radical rules that will show up in all of these problems, hence the name of the topic, right? If a lot of these will be familiar or completely solid to you already, feel free to skip the next few minutes of these videos, or this video, but these will be helpful to look back on because they will all show up. So, let's start up here. Just so everyone's aware of the terminology, the number or value that is being raised to an exponent, we're going to call the base number. Okay? And then this number up here is the exponent, of course. So, here we have a to the m times a to the n. They have the same base, but different exponents. All you do in that situation to combine them, when you're multiplying them together, is to say, okay, this is going to be equal to a to the m plus n. So you add these exponents. For example, just to show that this works, let's say you have 2 to the first times 2 squared. We all know the answer to this already. We could say, okay, 2 times 4, it's going to be 8. But if these were huge numbers, all you would have to do is say, okay, they have the same base, so I'm going to add the exponents. So this is equal to 2 to the 1 plus 2, or 2 cubed, which we also know is 8. So that just shows it works. Okay, moving on, a similar idea. A number raised to an exponent, divided by the same number raised to a different exponent. All you do is subtract these exponents. And I'll show you why that works once we get down a little further. When you have a number, a base, raised to an exponent, in parentheses, raised to another exponent, to combine them, you just multiply them together. Next, we have 2 numbers raised to the same exponent. Now that's the same thing as saying the first number raised to the exponent times the second number raised to the exponent. And same goes for down here. We have a divided by b to the m. That's the same as saying a to the m divided by b to the m. You just distribute the exponent in. When you have a one-term expression inside the parentheses, once you get to multiple term expressions in the parentheses, it gets a lot different, but that's not what we're getting into now. So, down here, we're going to revisit this idea back up here, whereas a to the m divided by a to the n is equal to the a to the m minus n. So, ignore that for a second. A to the negative m is equal to 1 over a to the m. When you have a negative exponent, essentially what that does is it flips it. So you would have the reciprocal of it. Let's say you have 2 to the negative 2. That's the same as saying 1 over 2 squared, which is equal to 1/4. You can get into larger exponents as well, and larger numbers, and still it works. Even if you said 3 over 5 to the negative 3, all you would do is distribute the 3 and then flip it. Or you could say distribute the negative 3 and switch the denominator to the numerator and the numerator to the denominator. So this would end up being equal to 125 over 27. And let's revisit this idea up here. A to the m divided by a to the n is equal to a to the m minus n. Well, if you think about it, you have a to the m, a to the n. If you rewrote this and having a 1 on the bottom, so if you bring the a to the n term to the top, that's the same as writing a to the m times a to the negative n, because you just flipped it. You brought it from the denominator to the numerator, so you make the exponent negative. And now it's a multiplication problem up here. You multiply and add the 2 terms together. M plus negative n is the same same as m minus n. So that is how that works. All right, let's move on from exponent rules and go into radicals rules. These are very intertwined, and you'll see what I mean in just a second. So here we have a to the m divided by n. I'm going to write that again over here. A raised to the m over n. That is the same as saying take the nth root, so our denominator, of a to the m power. And what this means, this equality statement means, you can choose to do either one of these first. You can take a to the m first and then find the nth root, or you can find the nth root of a and then raise it to the m power. Just either way works. And know that if you have any sort of radical, you can turn it into an exponent. So for example, let's say you have the square root of 3. And you want to rewrite that as an exponent because it's going to help you solve the problem. You can say, okay, well, the square root, that is the second root, right? And we're raising 3 to the first power. So we take our exponent here, that's our numerator. We say 3 to the 1 over a root, which is 2. 3 to the 1/2 is the same as the square root of 3. Okay, the next one is just some distributing. So we have the m root of a times b, and that's e, and you can split that apart and say, okay, m root of a times nth root of b. Pretty straightforward. Again, same principle down here. We have the mth root of a divided by b is equal to m root of a divided by the m root of b. I'll write that a little bit more clear out here. So let's say you have the square root of 25 over 9. Okay? You can also split that up to solve it and say that is equal to the square root of 25 over the square root of 9. So now you can simplify it to 5/3. Okay, with that out of the way, let's move on to some actual problems. All right, here's our first problem of the video. A lot of these 3-pointers are going to be pretty straightforward if you know your exponent and radical rules. So this first one's a pretty great example, just applying our knowledge. Find a plus b if m is not 0, given that m to the 3rd power to the 2a power is equal to the m to the 54th power, and m to the b times m to the 2b times m to the 4b is equal to m to the 28th. Okay, let's start with our first equation here. We have m cubed to the 2a is equal to m to the 54 power. So first things first, I'm going to simplify this. I'm going to say m cubed to the 2a is the same thing as m to the 6a. Right? Because if we have a base raised to an exponent raised to another exponent, you multiply those two exponents together and you have an equivalent expression. Now, we have a base raised to an exponent, a base, that same base raised to a different exponent. Well, we know that for these to be equal, since they have the same base, their exponents are also going to have to be the same. So, I can say that 6a is equal to 54, because we know that those exponents are going to have to be the same. Now all we have to do is solve for a, and we know that a is equal to 9. Now, let's do the same thing for b. We have m to the b times m to the 2b times m to the 4b is equal to m to the 28th. Well, these are all multiplied together. They have the same base, but different exponents. So when we multiply them together, all you have to do is add their exponents. So we would end up getting m raised to the b plus 2b plus 4b, which is m to the 7b. And that's still equal to m to the 28th. Again, we have a base. It's raised to a different value on both, well, we know it has to be an equivalent value on both sides for them to be set equal to each other. So we can say 7b is equal to 28. So we know that b is equal to 4. Now, it's asking a plus b. All we have to do is 9 plus 4, and that gives us our answer of 13. Okay, here's our next problem. If 9 to the 6th times 27 to the 5th times 81 to the 4th is equal to 3 to the x, find x. Okay, well, the first thing that jumps out at me is that, 9, 27, 81. Those are all powers of, those are all powers of 3. So, let's think about what we did in our last problem. We had numbers of the same base raised to exponents, so we could set those exponents equal to each other. In this case, that's going to be really helpful because we're trying to solve for an exponent. So, on this side, we want to be able to combine them all and have the same base, a base of 3. So what I'm going to do is to turn each of these terms into a 3 raised to an exponent. So, let's take 9 for example. We know that 9 is equal to 3 squared, and that 9 is raised to the 6th. Okay, we have 27. 27 is 3 cubed. We'd say 3 cubed raised to the 5th. Finally, we have 81, which is 3 to the 4th raised to the 4th power. That is equal to 3 to the x. Now let's simplify. Okay, 3 squared to the 6th. Well, we multiply these two exponents, so we can say this is 3 to the 12th times 3 to the 3 times 5, so 3 to the 15th, times 3 to the 4 times 4, 3 to the 16th is equal to 3 to the x. Now all we have to do is multiply these together. Okay, so we add our exponents. 3 to the 12 plus 15 plus 16. Because when we multiply, we add our exponents together. So we have 3 to the 12 plus 15 plus 16 is 43. And so we get that 3 to the 43rd power is equal to 3 to the x. So we can say x is equal to 43, and that is our final answer. All right, find the positive value of n so that the square root of 2 to the n squared is equal to 256. All right, this is a little scary to look at first. You have a square root in here, you have an exponent raised to an exponent, and then you have a pretty large number over here. So, let's just start out by thinking about what we've done in the last few problems. We have ended up getting our exponents to be set equal to each other because they share a base. Well, we know that 256 is a power of 2, and we know that the square root of 2 is the same as 2 to the 1/2. So I'm going to write both sides of these equations with a base of 2. So we have 2 to the 1/2, because that's the square root of 2, raised to the n squared, equal to 2 to the 8th. Okay, now let's multiply these exponents together. 2 to the n squared divided by 2 is equal to 2 to the 8th. Now we have our bases equal to each other, so we know that our exponents must also be equal to each other. So we can say n squared over 2 is equal to 8. Multiply both sides by 2, you get n squared is equal to 16. So, take the square root of both sides, that n is equal to 4. And that is our final answer. Alright, here's our first 4-pointer of the video. A to the 2/3 times b to the 1/4 times c to the 7/5 is equal to the nth root of a to the x times b to the y times c to the z. Find the number which is the sum of n plus x plus y plus c. Alright, taking a little step up already. First things first, I'm going to find a common denominator for all of these exponents. The reason why I'm doing that is because these numbers here are all taken to the nth root. And we know that if we have a fractional exponent, the denominator is the root that is being taken of that number. For example, 2 to the 1/2, well, that's the square root of 2. So they're all it's all the same number, so we have to find the least common multiple, or the least common denominator in this case, of 3, 4, and 5. The least common multiple of 3, 4, and 5 is 60. So let's rewrite all of these numbers with the exponent, the denominator of that, being equal to 60. So we have a to the 2/3. And if we're trying to get that to be a raised to something over 60, well, 3 times 20, 2 times 20, so we get a to the 40 over 60. I'm just going to do these next few because I believe that all of you can multiply out and get the right fractional exponents. Alright, now that we've done that, we know that our n value is equal to 60 because that's the denominator of all of these exponents, and that's the root to which all of these numbers are being taken. So I can already say n is equal to 60. Now we have a to the x. Well, all of these numbers are going to be the numerator to which all of these numbers are raised to. So we have a to the x, so that's going to be a to the 40th power. So we know that x is equal to 40. Same applies for the rest of them. The numerator of b is 15, so we know that y is 15. C, the numerator is 84. Z must be equal to 84. Now, we add these all up, we get 100, 99. So, our final answer of n plus x plus y plus z is 199. Alright, here's the next problem. Quick disclaimer before we start, there are so many different ways to go about it. I'm just going to show you one that I think is probably the most simple and straightforward way to do it. But whatever works for you, great, as long as you get the right answer. Find the positive number x such that x to the 6th is equal to 12 cubed times 15 cubed times 20 to the 6th, all over 125. Now first, let me just point out the positive number x. Yes, this is important. It is important to know this because x is being raised to an even exponent. So any number, positive or negative, raised to an even exponent, you're going to get an even answer. So technically, there is going to be a plus or minus x. But this situation, they're just asking for the positive number. So that makes it a little bit easier. Or easier to think about. So, first, I'm going to start by rewriting this equation. And I'll explain to you what I'm doing as I do it. So I'm going to leave. So I'm going to rewrite x to the 6th as x cubed squared equal to 12 cubed times 15 cubed times 20 cubed squared. So hopefully you all see how I just split up the 6 here. X cubed squared is the same as x to the 6th because you multiply these exponents. We're going to write all over 5 cubed. Because 5 cubed is equal to 125. So, now that we have this, you can see a common exponent here. We have a cubed on every single one of these terms. So I'm going to take the cubed root of both sides of this equation. So you can say, so it cancels out here, but we still have a 2 left over. So that is going to be x squared. Or if you kept it as x to the 6th, you could say, okay, our numerator is 6, our denominator is 3, because we're taking the cubed root. 6 over 3 is squared, so that leaves you with x squared. Over here, Well, we know that we can split each of these terms up and take the cube root of those individually. So, cube root of 12 cubed is 12 times cube root of 15 cubed, 15, times cubed root of 20 cubed squared. Well, we do the same thing we did over here. Our cubes cancel out, leaving us with a 2. So we have 20 squared over 5. Okay, now we're here. Well, it's very tempting to immediately just take the square root of both sides. And yes, we are going to do that because we are solving for x. But first, I'm just going to cancel the 5 out on the bottom. It makes it a little simpler so we don't have to multiply all these together. So we have 15, and we're canceling out the 5, so we have a 3 on the top and a 1 on the bottom. So x squared is equal to 12 times 3 times 20 squared. Okay, most of you probably noticed, oh, 12 times 3, 36, another square number. Perfect, let's take the square root of both sides. Now, if it wasn't that simple, if you had a lot more multiplying to do before you got to that, what you could do is, let's take the prime factorization of 12 here. That's going to be 2, 2, and 3. Notice if we rewrite 12 as 2 times 2 times 3, we can say, oh, 3 times 3 here, another square number. 2 times 2 here, another square number. That's perfect. So, we could rewrite this and say 2 squared times 3 squared times 20 squared, take the square root of all that, and multiply. Or, the more straightforward and simpler way, say multiply 12 times 3, get 36. So now you have x squared, bring that right up here, x squared is equal to 36 times 20 squared. Take the square root of both sides, and we're only looking for our positive answer. So you have x is equal to 6 times 20, or x is equal to 120. That is our final answer, and if you did it another way, if you even used this method, you would still get the same answer. Alright, here's our last 4-pointer of the video. Solve for x. 81 over 625 raised to the x minus 2 is equal to 125 over 27 raised to the 5 minus 2x. Well, okay, that's a lot. We have a lot of big numbers, and we, of course, have variables in the exponents again. So, like we did last time, or not last time, but many times before this in all the problems, let's try and find a common base so we can set our exponents equal to each other. Okay, so, first thing that I notice, okay, 625, 125. Powers of 5, 81, 27, powers of 3. So I'm going to rewrite both of these in terms of powers of 5 and powers of 3. So we can write 81 over 625 as 3 over 5 to the 4th. Because if you split that up, 3 to the 4th is 81, 5 to the 4th, 625. Let's not forget our exponent, x minus 2. So the same thing over here. I'm going to rewrite this as 5 over 3 raised to the 3rd raised to our 5 minus 2x. Okay, so now that we have that, let's multiply our exponents together so we have one single exponent. 3 over 5, 2v4x minus 8 equals 5 over 3 raised to the 15 minus 6x. Okay, so it's very tempting to say, oh look, let's set our exponents equal to each other, we have the same base. Not yet. We have 3 over 5 and 5 over 3. But if you remember what you have to do to flip your base, you'd have to turn your exponent negative. So, again, the reason why that is, we have 1 over 4 to the negative 1. flip it, becomes 4 to the first power. It's just the reciprocal. The negative exponent makes something the reciprocal of itself. So, 3 over 5, if I make our exponent negative, it's going to be 5 over 3 raised to the negative 4x plus 8, don't forget to distribute to both parts, equals 5 over 3 raised to the 15 minus 6x. Now we have our same base. Now all we have to do is a little simple algebra. Set negative 4x plus 8 equal to 15 minus 6x. Solve for x. Add 6x to both sides, you get 2x plus 8 equals 15. Subtract 8 from both sides, and we get x is equal to 7/2. And that is our final answer. Alright, here's our first 5-pointer of the video. Find all values of x such that the square root of 6x plus 5 minus the square root of 9x minus 2 is equal to 1. So this kind of problem is designed to trip people up, especially right at the end, and I'll show you what I mean when we get there. So, my first thought is, okay, let's square both sides. But to make it a little simpler for ourselves, let's move our negative 9x minus 2 over to the right so that when we square both sides, we don't have to FOIL these two together. That is not very fun. So, we bring the 9x minus 2 over, and we have the square root of 6x plus 5 is equal to 1 plus the square root of 9x minus 2. So now, we can square both sides and say, okay, square root of 6x plus 5 squared is 6x plus 5. And that's equal to, now we have to FOIL this. So we get 1 squared plus the square root of 9x minus 2 plus the square root of 9x minus 2, so 2, 9x minus 2. And then we have plus 9x minus 2, because the square root of 9x minus 2 squared is 9x minus 2. So now let's simplify as much as we can. I'm gonna bring our x to the 0 terms and x to the first terms over to this side, and leave our 2 times the square root of 9x minus 2 over here. So that ends up being negative 3x plus 6 is equal to 2 times the square root of 9x minus 2. Alright, let's square both sides again. We FOIL this side and get that 9x squared minus 36x plus 36 is equal to 4, don't forget to square your 2, times 9x minus 2. We distribute the 4 and get 36x minus 8. And we bring all this into one side so we can set it equal to 0 and factor from there. So bring all of this over and we get that 9x squared minus 72x plus 44 is equal to 0. So then we, of course, have to multiply these together and find two factors that add to negative 72. I already know that 9x squared minus, or 6x minus 66x plus 44. So negative 6 and negative 66 are the numbers that we want. We factor out the 3x over here, say 3x to 3x minus 2. And then over here, negative 22 times 3x minus 2 over here. So we have our factors. It's going to be 3x minus 22 and 3x minus 2. So x is going to be equal to either 2/3 or 22/3. It's very tempting to say, oh, here's our answers, great. But no, because we have square roots here and we squared both sides, we have changed this equation enough to say, okay, maybe some answers work for this, but they may not actually work here. So we have to plug both of these in to make sure that they work. So let's start with 2/3. We have the square root of 6 times 2/3 plus 5. So 6 times 2/3 or plus 5 minus the square root of 9 times 2/3, which is 6, minus 2 is equal to 1. Okay, we know 4 plus 5, 9, square root of 9 is 3, 6 minus 2 is 4, square root of 4 is 2, so 3 minus 2 is in fact equal to 1. So we know that this is one, if not the only one, of our answers. Now let's plug in 22/3. So we have square root of 6 times 22/3, so that gives us 44, plus 5, minus the square root of 9 times 22/3, which gives us 66. We know 44 plus 5 is equal to 49. Square root of 49 is 7. Minus square root of 66 minus 2, 64. Square root of 64 is 8. Does that answer 1? No, that is equal to -1. So we know that our only answer here is 2/3. Alright, here's the next problem. Solve for x among the real numbers. 4 to the 4x minus 4 to the 2x minus 2 is equal to 0. Okay, this is a little weird. You could start rearranging things, but it's not going to get you very far. So, one thing to notice is, well, this looks a little familiar. This kind of looks like a quadratic when you set 0 to factor, right? Well, you can turn it into one. We have 4 to the 4x minus 4 to the 2x minus 2. This can be our x squared term, this could be our x term, and this could be our x to the 0 term. The way that I'm going to do that is I'm going to say, okay, 4 to the 2x is equal to a. Okay, once I do that, well, we replace this with a, and this is the same thing as saying 4 to the 2x raised to the second power, so that's just going to be a squared. I'm going to rewrite this. A squared minus a minus 2 is equal to 0. Now, we can factor, okay, so things that multiply -2 add to -1. -2, or a minus 2 times a plus 1. So we know that a is either equal to 2 or -1. So let's come back here. We know that a is equal to 4 to the 2x. 4 2x is equal to 2. Okay, let's do what we've done before. Get the same base so we can set our exponents equal to each other. This I can rewrite as saying 2 to the 4x is equal to 2 to the first power. And we set our exponents equal to each other. 4x is equal to 1, so x is equal to 1/4. Okay, let's look at our other solution. 4 to the 2x is equal to -1. So we are raising this number to an even exponent. So there is no possible way that we can end up with a negative number. So we know that 4 to the 2x cannot be set to -1. Therefore, our only answer for x is 1/4. That was a lot simpler than I think the majority of 5-pointers are going to be. So that's great. And that is our final answer. All right, last but not least, here is our final problem. This one is one of my favorite kinds of problems. It looks kind of crazy, but once you see the solution, you'll think this is the most simple thing ever. So, what does the square root of 6 plus 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 ... equal? Okay, this goes on infinitely. Is there a sum? Yes, there is. There is an actual sum because it gets closer and closer to 0 every single time. So eventually, you will reach a point where it's so small that it's barely moving the number up at all. So there is an actual answer. So the first thing that I'm going to do is say, okay, this value, whatever it may be, square root of 6 plus the square root of 6 plus ... is equal to x. Okay, so knowing that, I can also say the square root of 6 plus x, this is the same thing over and over, if this is x, that still is the same expression, is equal to x. And you can look up here. If you take 1 away, it's still the same thing. So I can set that equal to x. Now, all you have to do is square both sides and say 6 plus x is equal to x squared. Bring the x squared over here, or bring the other two terms over with the x squared. We have 0 is equal to x squared minus x minus 6. So we have in factors form an x minus 3 times x plus 2. So we know that x is either equal to 3 or negative 2. This number is not going to be approaching a negative number. So our only answer here, our only solution, is going to be 3. So the square root of 6 plus the square root of 6 plus the square root of 6, our answer is 3. This was our video on meet number 3, topic number 2, exponents and radicals.
Thank you for watching.
I'm Iris.
And I'm Sebastian.
And we are the MAML Manual.